Okay, so today we'll start by having some small survey on graph miners theorem. So lecture 24, right? So far we proved that trees are well quasi-ordered by topological miners, and in the homework you will prove that not all graphs are well quasi-ordered by topological miners, but we're going to discuss the following. This is Robertson and Seymour from 1986 to 2004, and they prove that graphs are well quasi-ordered by the minor relation. So what does that mean? What does that mean? That means, right, by definition, that means that every infinite sequence of graphs, let's say G1, G2, G3, has a pair I less than equal to J such that Gi is isomorphic to a minor of Gj, or graphs are well founded, but actually graphs are well founded automatically, so we don't have to write that, have no infinite end chain. Okay, so what does that mean? So with respect to minors, so why is this interesting? So think of the following, right? So we say okay, let P be a class of graphs closed under taking minors and isomorphisms. So if I have one graph in this class, then any graph isomorphic to that graph is also in this class. That's what I mean by closed under isomorphisms. And also it's closed under taking minor. That means if I have a graph, then all its minors are in this graph. So this is property, so which called like minor closed. Property of graphs. Right, so here are some examples. Right. So for instance, graph is a set of forest. Right. This is a minor closed property of graphs because every minor of forest is a forest. Or like no edges. Okay, edgeless graph. Trivial classes, right? Or planar graphs. Every minor of planar graphs are planar, right? Or graphs embeddable on a surface of genus G without edge crossings. Right? That by the same logic, right? You can delete an edge, you can contract an edge, and those things preserve the property that the graphs are embedded on a surface, on a fixed surface. Right? So these things are all the property examples of properties that are closed undertaking minors. And this Lovson and Simmers theorem states that these properties are closed undertaking. I mean, these minors are well-quasi-ordering. So what does that mean? Okay, let's think of the following. Right. For vision, so for P means minimal okay, class, okay, what is it? Set of graphs such that G is not in P or proper minor of G are in P. Okay, so those are the minor minimal graphs not in P. But to be more precise, I want it to contain something like I want it to contain the okay, I mean it's not a good notation. Okay, let me okay, so now yeah, this is not a good notation. Okay, let me just say this way. For every minor closed property P, let X be the set of minor minimal graphs not in P. Okay, and with the property such that every X is minimal. Okay, all right. There's some slight issue. What's the issue? I want to say that X is finite, but it contains all the isomorphic graphs. Okay, so let me say it this way. Then we claim that X has finitely many graphs up to isomorphisms. So when you count isomorphic graphs as the same graph, then you only have finitely many graphs. Why? If not, what's wrong? If you have two graphs, let's say H1 and H2 in chi, then H1 is not isomorphic okay, let me fix this way. Yeah, so H is not isomorphic to yeah, it's not a minor of G. No, not G. H2. Why? Because if H1 is isomorphic, yeah, it's annoying to say isomorphic to a minor of H2, and H1 has the property, then H1 is not a proper minor. Okay, so whenever I say this, not isomorphic to a proper minor, so this means that H1 is isomorphic to H2, right? Because each of these graphs in this this list, set of minor minimal graphs, not in P, none of them is a isomorphic to a minor of another. So in other words, chi is an anti-chain, right? And Robertson-Simers theorem states that this is finite, right? So therefore, here's a corollary. For every minor closed property P of graphs, there exists a finite list G1, G2, Gm of graphs such that G is in P if and only if G has no minor isomorphic to Gi for each I. So the important thing is this finite, right? If I replace this minor closed property by topological minor closed property, then you still get a list, but this list is going to be infinite depending on the property. So only this minor property has this nice characterization. So why is this interesting? Probably I mentioned it already. So when it's planar, then you only need the two graphs, K5 and K33. This is Grotowski's theorem, right? And for each graphs embeddable on a surface, this theorem says that there is a finite list. Okay? So the thing is, this finite list is not generated by the proof of graph minors theorem. So how does it work? So we have seen that trees are well quasi-ordered by topological minors. So the B sketch, right? So it's built on, right? So initially there's a Higman's lemma, and then there's a Kruskal theorem, right? Trees are well quasi-ordered, and then Robertson and Simers, what they did is to prove that graphs of bounded tree width. So these are the graphs which are close to trees. I'm not going to be very precise now, but graphs of bounded trees, you can think of it as something like trees, but slightly thick, more thick. Yeah? So tree width 1 graphs are precisely trees, forest. And by using this Kruskal theorem, Robertson and Simers proved that graphs of bounded tree width and most k are also well quasi-ordered by minors. Now, suppose we wish to prove the graph minor theorem, then we can assume, suppose that we have a infinite sequence of graphs such that no Gi is isomorphic to a minor of Gj for all I less than or equal to j. Suppose that's the case, right? Right? If graph minus theorem is false, right, then you must have a bad sequence, and the bad sequence is something like this. Now, this implies that G2, G3, G4, all of these graphs have no minor isomorphic to G1, right? Because the first graph cannot be a minor of any graph in the sequence. Now, let me tell you a simple case. If G1 is a triangle, or let's say, let me say, if G1 is a loop, then it's a single graph, not a set. Then G2, G3, it's not a proof yet. I mean, not at all a proof. These are all forest, right? And then we know that trees are well-quasi-ordered. By Kruskal theorem. And then if we apply Hickman's lemma, then the disjoint union of trees are also well-quasi-ordered. So that means forests are well-quasi-ordered, right? So no bad sequence exists, right? So this is the simplest case. When in the bad sequence, if the first graph is a single vertex graph with one loop, then we know that all graphs appearing later can be assumed to be a forest, because otherwise it's not a bad sequence. And then since those graphs are forest, we can use Kruskal's theorem and Hickman's lemma to say that such a sequence doesn't exist, so it's not a bad sequence. So depending on the graph, in the first graph, we can do something. And right, so are you with me? I'm trying to explain the sketch of the proof for graph minors. Right, so where is it? Yeah, I'm trying to show you the sketch of this theorem. Now, if the first graph is a planar, then what can it say? Actually, there's a theorem, again due to Robertson and Simmer. They said that if okay, let H be a planar graph, then there is a constant depending on H, such that every graph with no minor isomorphic to H has tree width at most C of H. That's Robertson-Simmer's theorem. And if this is the, so I didn't say what tree width is, but this just means that if you forbid the planar graph as a minor, then the graph is essentially like a trees. Not exactly a tree, but it is like trees. So in that case, another lemma of Robertson and Simmer in 1980s, I think, is that graphs of bounded tree widths are well-quasi-ordered. So tree width is just number. So each graph has some number. If graph is forest, then tree width is 1. If graph is like complete graphs on n vertices at tree width n minus 1. And they prove that these are well-quasi-ordered by minors. So by combining these two, we know that if the first graph G1 is planar, then we win because there's no bad sequence. Because all graphs G2, G3, G4, all of them will have a small tree width, and if they have small tree width, they are well-quasi-ordered. So we may assume G1 is non-planar. Okay. Now what they use is the following, like G1 is a minor of kt for some t. Right? Now Robertson Simmer also did the structure, describe the structure of graphs without kt minor. So what are they? So for fixed t, if you don't have a complete graph of t vertices as a minor, it can be built from graphs embeddable on a surface of bounded genus, because graphs on a bounded genus cannot have large complete graphs embedded without crossings. But then there are certain things. Maybe you might have a small number of vertices outside adjacent to all of them. Like they could, so this number of them is small, some constant. The genus is some constant. And there's also some structure called the vortices, which I'm not going to describe, but on the surface you have some cycle where inside of cycle has a particular structure, something called vortices. These are called apex vertices. So you have a graph like that, and these graphs doesn't have a large complete graphs. It could have a kt. I'm not saying that this graph doesn't have kt, but I'm saying that graphs without kt, so this direction is also wrong, but graphs without kt can be built from this kind of blocks, building blocks. So this is one building block. This block doesn't have a really large clique, right? Because surface doesn't have a large clique, and having small number of apex vertices and small number of vertices will not change much. So the size of largest clique minor is bounded. And then what you do is, like, you have these surfaces, right, with the apex and vertices, and these things are glued together as a tree-like structure. So when you glue these graphs, you use take a click on complete graphs on both sides and then glue them. So you do that in a tree-like structure. So I'm not very precise, but basically any graph without complete graph minor, complete graph on t vertices as a minor, can be built from graphs embedded on a surface of bounded genus by adding small number of apex vertices, and then you glue them by a tree-like structure. So once you have a tree-like structure, then it's quite easier to work with the Kruskal's theorem, right? So as long as each building blocks are well-quasi-ordered, then you can use Kruskal's theorem with some extension, right? You can label edges or vertices of the trees to have a well-quasi-ordering. So that kind of technique is used. But the proving this structure theorem takes a lot of pages. So it's one of the most difficult and deepest theorems in the graph theory. All right, so that's the sketch. So I'm not telling you any part of the proof, just a big picture. So why is it interesting? Why is this useful? So here's a theorem, another theorem by Robertson and Simmer. 1995 for fixed graph H. There is a polynomial time algorithm to decide whether an input graph has a minor isomorphic to H. So that's their theorem. So for any graph H, let's say I fix K5, and then they have an algorithm that runs in a polynomial time. Polynomial time means that the running time depends on the polynomial of the size of the input graph, where the size means the number of vertices plus number of edges. Right. So you can run this algorithm to decide whether or not the input graph contains H as a minor. And I think the running time was previously Robinson-Simons result was something like n cubed, but the current best is probably something like n log n. And by Kawarabayashi and Reed. Okay. I don't remember whether this paper is published already or not. So, if we combine two theorems, combine the graph minors theorem together with this algorithm, then we have nice corollary. For every minor closed property P, there exists a polynomial time algorithm to decide whether an input graph has P. Okay, so for any minor closed property of graphs, there exists a polynomial time algorithm to decide whether an input graph belongs to P, and the running time is even n log n. So this is surprising. So, for instance, planar graphs. We know how to decide whether a graph is planar just by going through the Grotowski's theorem, the proof of Grotowski's theorem. But this corollary says that there exists an algorithm. Okay, there exists an algorithm to decide whether graph is planar. All right, so why is this interesting? Yes, Grotowski's theorem. For planar graphs, you have an algorithm. For any other graph property closed undertaking minor, you have an algorithm. No, I cannot say you have an algorithm. There exists an algorithm, right? So there's some example which is non-trivial. So here's one example. So a graph is linklessly embeddable. In R cubed. So if it has an embedding in which no two disjoint cycles form a link. So what is a link in the three-dimensional space? It looks something like this, right? If you have two cycles making a link, then we say then it is a link. I mean, if one cycle in the three-dimensional space, and there's another cycle in the three-dimensional space, and if they form a link, then we say it has a link. But if they don't form a link, if you can separate these two cycles by continuously moving it without crossing, then we say it's linkless. And a graph is linklessly embeddable if no two cycles form a link. Now, this property is closed on the taking minors, right? Because contractions in a three-dimensional space still works like a contraction in a planar graphs. You can contract, and that still works. When you delete an edge, linkless embedding is still linkless embedding. So this is a closed undertaking minor. So by Robertson-Zimmer's theorem, there must exist a finite list of forbidden minors. So this list is typically called forbidden minors. And actually, this is true. So this is, they even found a list, Robertson, Zimmer, Thomas in 1995 says that a linkless embeddable if and only if no minor isomorphic to one of the 7 graphs. So one of them is Peterson graph. And then the others are similar to Peterson graph. So for instance, so what I did is replace this vertex by a triangle. So this is oh no, not this triangle. Okay. Yeah, I think that's correct. So this is y delta operation because what you look like y become delta. The y is this way. So any graph obtained by this y delta operations are in the forbidden minors, and what they proved is that this is called the Peterson family. So linkless embeddable graphs are precisely graphs without those 7 graphs as a minor. So in this case, we are good. So this implies that you can use minor testing algorithm to decide whether or not graph is linklessly embeddable by testing these forbidden minors. But this doesn't mean that this algorithm will find an embedding, right? If you use graph minors theorem to say some property holds, it just gives you yes/no answer, right? If it's a yes, that just means that there's no forbidden minors. That doesn't mean that you have an embedding. Right? Embedding is not automatically given. Right? If I use Grotowski's theorem to say the graph is planar, if I only use Grotowski's theorem as a black box and say, oh, this graph doesn't have K5 minor and K33 minor and therefore it's planar, this is true. But if someone asks you the embedding, planar embedding, then you have no idea. You have to do some other things, right? Maybe going through the proof of Grotowski's theorem. But this linkless embeddable graphs, I don't know whether you have an algorithm to embed it precisely. Probably there may be something. Now, let me tell you a more complicated case. So, non-linearly embeddable. So, non-linearly embeddable graphs are graphs. It's linked list. So, non-linearly embeddable means that has an embedding in R3 that is linked list and no cycle is a NAT. What is NAT? So there's an unnat and NAT. So unnat is something like this. Something NAT is like something like, oh, I don't know whether I'm drawing correctly. Something like this. No continuous operations to move this thing will make it up to a NAT, right? Is this a NAT? Yeah. So this is an example of NAT, right? So if you have a simple closed curve which you cannot deform it into a single circle, is a NAT. So non-linearly embeddable means you don't have two cycles forming a link and you don't have any cycle forming a NAT. And this is also closed undertaking minor, and there's a big open problem. What are the forbidden minors? For non-linearly embeddable graphs? No one knows. Another open problem, do we have any algorithm, we don't care about the running time, any algorithm to decide whether a graph has graph is non-linearly embeddable. So here I want to emphasize that do we have. Okay, what do we mean? What do we mean? As a corollary of Robertson-Simmers theorem, there exists a polynomial time algorithm to decide whether a graph is non-linearly embeddable. Why? Because the list of forbidden minors is finite, and you can use the algorithm to decide minors to check one by one. And for each of the forbidden minors in the list, you decide whether this is a minor or not. Now, the problem is that the list of forbidden minors is not provided by the Robertson-Simmers theorem. Robertson-Simmers theorem says that such a list exists. We don't know, right? So we know that there exists an algorithm, but we don't know. We don't have that algorithm because we don't know the list of forbidden minors. That's why I wrote, do we have? I mean, do we have? And we don't have such an algorithm because we don't know the list of forbidden minors. And if there's a way to generate them, then that would be convenient. But so far, we don't even know how to generate them. Okay, so there's a distinction between. So it's an interesting distinction between there exists something or we have something. So Robertson-Simmers theorem is once strange case where there exists a polynomial time algorithm to decide something, but we don't have such an algorithm because we don't know the list of forbidden minors. All right, so that's it. Right, so we have 2 more weeks to go, and the plan is to cover the Matroid theory for last 2 weeks. The goal is to prove this Nash-Williams theorem. Remember that when we proved the Noether flows, we had one theorem which we didn't prove anything. The theorem was that if you have a certain edge connectivity, 2k edge connected, then you have a k edge disjoint spanning trees. We use that to prove that every graph without cut edges have Noether A flow. Now, there are proofs using only the graph theory, but once you see the proof things in Matroid theory, it will be a lot easier as soon as you see the Matroid theory. So that's the plan for the last remaining of this course. So new chapter. Matroid theory. So what are the Matroid? So this was invented by the American mathematician whose name is Whitney, 1935. The paper is well written. It's on a it's written in English and it's well readable. So the examples. Let me show you the examples. So GBA graphs, and let's think of the set of edges which doesn't include any cycles. All right. Now, how big is I? How big is the graph? Well, what kind of property do we have? Then if x is in I, then number of edges is at most number of vertices of G minus number of components. Because if you have no edges, no cycles, then it's a forest. So edges, number of edges of forest is at most number of vertices minus number of components. Right? That's one known fact. And there are more properties. So what else? So if you have a same graph, two maximal sets in I have the same size, right? Let's think of the simple case. If you have a connected graph, now I look at the maximum set of edges having no cycles. What are they? These are precisely the edge set of spanning tree. And spanning trees have exactly n-1 edges when n is the number of vertices. So this is a strange property. You have a collection of subsets, and it has precisely same number of maximal sets have the same number of edges. And similar property happens in the vector spaces. Okay, so or matrices. Right? Think of the matrix. and the columns are indexed by some set I. No, not I, indexed by E. And then I is set of the column indices so that the column vectors corresponding to X are linearly independent. Now, this is again interesting fact that two maximal sets of linearly independent column vectors have the same size, which is the rank of the matrix, right? So every basis has the same size in the matrix. So these two things looks quite striking. They have a common, they share the common combinatorial features. So that's how the matroid is motivated. So it's a combination of linear algebra and the graph theory. So let me define what a matroid is. Matroid M is a pair EI of a finite set E and a collection I of subsets of E satisfying the following three axioms. So I1 just means that empty set is in I. So I2 means if X is in I and Y is a subset of I, no, Y is a subset of X, then Y is also in I, and I3 means if X, Y are in I and the size of X is less than the size of Y, then I can find so there is an element in Y minus X such that X union E is in I. So what does that mean? And we say X is independent in the matroid M if X is in I. So think of the linearly independent set of vectors. So empty set is linearly independent. If you have a linearly independent set of vectors and any subset is linearly independent, then if you have two sets of linearly independent vectors, and if one is smaller than the other, then you can find some vector in the y side so that you can add it and still linearly independent because the whole space has a small, the same dimension, right? I mean the whole thing has, so size of X is small, so definitely you must have some vector left over in Y, which you can add it to X and make independence. So that's the motivation. So this is the axioms, okay? So the X is independent. So one common example, okay, so we say dependent if it's not independent. Okay, so example, so the matrix, let A be a matrix whose columns are indexed by E, a finite set E, then let I be the set of subsets of E such that the columns in x are linearly independent, then EI is a matroid, and this is commonly called the vector matroid. Okay, we write this way, MA. Another example, as G is a graph and I be the set of edges where X includes no cycles. So I have seen it already, includes no cycles. Then this thing, the set of edges with this set is also a matroid, and this is called the cycle matroid, and we write MG. So why is there matroid? Because first two axioms are easier. If you have a set of edges without cycles, then no subset has just cycles. What about third axiom? If you have two sets of edges, X and Y, both are forest, and X has less number of edges. Now, if there's a vertex in Y, right, which, so this is actually easy exercise. So let me show you the simplest case. If there's a vertex incident with edges in Y, which is not incident with X, then I'm happy I can just add this into X and still maintaining the property that X has no cycles. So I can assume that every vertex of Y, every vertex incident with at least one edge of Y is incident with X. But then the number of edges of X is smaller than number of okay, is this a good proof? Yeah, so right, and if X, and also there's a issue. So if I have a edge crossing two components, so this is a component of X, and if Y has such an edge, then we win, because I can add this edge without creating any new cycles. So that means every component of Y is a proper subset of, we can assume that every component of Y is a proper subset of component of X. Now use counting, right? So number of edges of Y is at most by, we know that number of edges in the tree is bounded by number of vertices minus 1 if graph is connected. So this implies that number of edges Y is less than or equal to number of edges of X. Contradiction. So it's again easy exercise. Okay, so these are two examples. Right, so in the next lecture we will continue describing a few terminologies, and these will be used to prove the Matroid theorem, which will imply Nash-Williams theorem. Okay, so that's it.